We are trained to picture a corporate data breach as a loud, chaotic event, red flashing lights, frantic typing, and hackers breaking through firewalls. But a modern data breach looks exactly like this: a quiet, well-lit desk on a Tuesday afternoon. The real vulnerability is a high-performing employee staring down a massive deadline. This is the software engineer under pressure to debug proprietary code, or the financial assistant struggling to format regional performance metrics before a board meeting. To finish the task, they copy thousands of lines of documented source code or a spreadsheet of unannounced revenue figures and paste it directly into a free public AI web tool. The AI generates the fix instantly. On the surface, the task is done hours ahead of schedule with perfect results. But that immediate speed is a distraction. It masks a transactional exchange where the employee trades corporate intellectual property for a temporary individual boost in output. Traditional malware trips network alarms because it forces its way in. This bypasses legacy perimeter defenses because the user initiates the transfer themselves. The data leaves the corporate network undetected, flowing through an encrypted channel as perfectly legitimate web traffic. This is voluntary exfiltration. A worker, driven by aggressive timelines, bridges the gap between secure internal storage and the public cloud, trading the company's long-term exclusivity over its data for a few hours of saved labor. Once that data lands in a multi-tenant public AI cloud, it is governed by consumer terms of service designed for data harvesting. In a traditional computer system, removing that file would be a mechanical process of wiping a server or a hard drive. But large language models do not store information in folders or databases. When data enters a public training pipeline, it is irreversibly broken down. Those pieces are distributed across billions of numerical parameters known as weights. Your proprietary source code or financial projections are now fused into the mathematical fabric of the neural network. Deleting a chat history or a user profile only hides the data from your view. Because your information is embedded in the network's weights, the only way a vendor can truly remove it is to scrap the entire model and retrain it from scratch, an action that costs millions of dollars. Once your data enters the weights of a public model, the enterprise surrenders exclusive jurisdiction. The information remains in the system, waiting to be reconstructed and surfaced when another user, potentially a direct competitor, crafts a prompt that triggers those same mathematical pathways. Discovering these leaks requires looking for quiet anomalies. A firm might notice a sudden spike in outgoing data traffic, or in more severe cases, find their own unique software logic appearing in public research logs. Once a potential leak is flagged, the IT team cannot rely on standard antivirus logs. Instead, forensic engineers must pull historical logs from the corporate proxy servers to see exactly what left the network. By decrypting the outward-bound data stream at the network perimeter, they reconstruct the exact payload. They can read the precise text fields and attachments to determine if the leak contained raw code, exposed customer records, or unannounced financial balances. To find the source, the security team must match the precise timestamp of the public AI query with internal network logs. This allows them to trace the connection back through the building, down to the exact internal IP address and the specific physical workstation that initiated the transmission. While an endpoint trace allows the company to terminate session tokens and close the gap, it cannot claw the data back. In this environment, reactive security is a clinical exercise in damage control rather than protection. Since data cannot be retracted from a neural network once it has been ingested, security depends on structural containment. Organizations typically lose control when they allow employees to operate on the operational edge, the fragmented landscape of unvetted consumer web tools. These tools are isolated silos that provide temporary speed, but offer no architectural integration or data security. This chart illustrates the financial framework required to fix this vulnerability, the 90-10 rule. Instead of paying for hundreds of disparate software licenses that create data liabilities, a company concentrates 90% of its budget on building its own enterprise core, a proprietary infrastructure that keeps all data processing inside a secure perimeter. The enterprise core replaces unvetted web tools with secure, private sandboxes. Employees still get the speed of generative AI, but their queries route into a ring-fenced environment completely isolated from the public internet. These sandboxes interact with foundational models through zero data retention APIs. This enterprise-grade channel creates a technical boundary. The data is processed in volatile memory to generate an answer, and is then instantly expunged. The vendor is legally and technically barred from archiving the input or using it for training. The final layer is an active defense. Companies deploy data loss prevention firewalls that analyze outgoing data in real time. If an employee pastes proprietary code or customer emails into an unauthorized public portal, the firewall intercepts the packet and kills the transmission. By concentrating resources in the core, the organization builds a durable, proprietary asset. The AI reads the company's data in real time to generate accurate, contextual answers, but the information never leaves corporate jurisdiction. In an economy where data is the primary driver of corporate valuation, control over that data is a fiduciary duty. If you do not own the core infrastructure that processes your information, you do not own your business.